Waals equation. We have used the ideal gas equation to model the behavior of an ideal gas. But can an equation of state describe both liquid and vapor behavior? This is the ideal gas equation. PV is equal to RT. If we have constant temperature, then P is equal to a constant C divided by V. Experimentally, we can approximate this by putting the cylinder in contact with a constant temperature bath. Then as we compress it, the pressure is going to increase. We can show this process by an isotherm on a PV diagram. And the shape of the isotherm is that of a hyperbola, which is a constant divided by V. We can look at the PV diagram for an ideal gas and compare it with that of an isotherm for a real substance. What we see is that the ideal gas equation predicts the behavior of the vapor, but it is quite unlike what the behavior of the liquid or the liquid plus vapor region look like. So what are the simplifications made by the ideal gas model that it fails when we are trying to model a liquid? First of all, in the model we assume that molecules are point masses, but in reality they actually occupy some space. Next, we neglect intermolecular forces, but these become significant when the molecular spacing becomes small. This happens when we have high pressure or when we have low temperature. Let us see if we can make corrections to improve the predictions made by the ideal gas equation. The ideal gas equation is given by P is equal to N RUT divided by V. Let us say we have a gas that occupies a volume V and the number of moles is N. Now, if instead of having point masses, we assume that they have some finite volume, then let us say that the volume occupied by the molecules in 1 mole of gas is B. The volume occupied by the molecules in N moles of gas, therefore, is N times B. So the volume that is available for movement of the molecules is not V, but it will be some V minus NB, where NB is the volume occupied by the molecules themselves. So we can make a correction to the ideal gas equation and write it as P is equal to N RUT divided by V minus NB. Next, we have to account for intermolecular forces. If there's a molecule in the center of the gas, it is pulled equally by other molecules on all sides. So the net force is going to be 0. If there's a molecule which is close to the wall, then it is only pulled back by the other molecules. So the force is not uniform, but in one direction, pulling it away from the wall. The pressure exerted on the wall by the collision of the molecules is therefore reduced due to intermolecular forces. Now the force on the wall is going to be proportional to the molecular density, which is N divided by V. The force which is pulling back the molecules is also proportional to the molecular density, and this would be the density of the molecules which are right behind those that are at the wall. The reduction in pressure, therefore, is proportional to the molecular density square, which is N upon V whole square. So now we can put corrections in the ideal gas equation of state. So first we have the equation of state corrected for the molecular volume. P is equal to N RUT divided by V minus NB. Now we add the correction for the pressure reduction due to intermolecular forces. And we reduce the pressure by A, where A is a constant of proportionality, times N upon V whole square. This is what we call the van der Waals equation of state. If we now define a specific molar volume, V bar, which is the volume V divided by N, the number of moles, then we can write the van der Waals equation as being P equal to RUT divided by V bar minus B minus A upon V bar square. Rearranging it, we can write it in the form P plus A upon V bar square times V bar minus B equal to RUT. Now, A and B are known as the van der Waals constants, and they are the properties of each different gas. Now, the van der Waals constants can be measured experimentally, or they can also be derived analytically, and we'll come back to that and talk about how we can do that. But this is a table which gives values of van der Waals constants for some common substances. Let's see how the van der Waals equation behaves as we go to the limits of either very low pressure or very high pressure. At low pressure, the volume is going to become very large. So we'll say V bar tends to infinity. If we now substitute this into the van der Waals equation, then that first term, A upon V square, go to 0. Also, if V bar is very large, then V bar is much greater than B, and we can neglect B. We then have what is the ideal gas equation. PV is equal to RUT. Now let's look at the high pressure limit. So we have the van der Waals equation. We can rearrange it to write it in this form. So V bar minus B is equal to RUT divided by P plus A upon V bar square. At high pressure, let's say that P goes to infinity. The denominator in this term, P, becomes very large, and so therefore that term goes to 0. In which case, V bar is equal to P, a constant. If the specific volume is a constant, then that is an incompressible liquid. So this is an isotherm for a real substance, and we can see that the van der Waals equation approximates it at both high pressure and the low pressure. At low pressure, the equation becomes the ideal gas equation. At high pressure, it becomes the equation for an incompressible liquid. To summarize, we have derived the van der Waals equation P plus A upon V bar square times V bar minus B is equal to RUT. This equation accounts for intermolecular forces and the volumes of molecules. In the low pressure limit, it behaves as an ideal gas, and in the high pressure limit, it behaves as an incompressible liquid.